Hello, everyone, and welcome to today's presentation. I'm excited to have you here as we explore the role of the fire alarm and fire suppression design engineer. The goal of this session is to help you understand system design, key codes, and the installation process. We'll be covering the main NFPA codes involved, including NFPA 13 for sprinklers, NFPA 14 for standpipes, NFPA 20 for pumps, and others like NFPA 22, NFPA 25, NFPA 72, NFPA 92, and NFPA 2001. So, over the next few slides, we'll dive into these topics to give you a comprehensive overview. Let's get started. Let's take a closer look at the different types of fire protection systems outlined here. First, we have the fire alarm system, which is governed by NFPA 72. This system is essential for early detection and alerting occupants in case of a fire. Next is the sprinkler system, covered under NFPA 13, which automatically activates to suppress fires and minimize damage. Then we have fire pumps, according to NFPA 20, which are crucial for ensuring adequate water pressure and flow to these sprinkler systems. Fire tanks, regulated by NFPA 22, store the water needed for fire suppression, especially in areas where municipal supply isn't reliable. Piping and valves, covered under NFPA 14 and 13, connect and control the flow of water throughout the system. Smoke exhaust systems, under NFPA 92, help remove smoke from buildings, improving safety and visibility. For specialized needs, we have clean agent systems, like FM 200 or Novik 1230, covered by NFPA 2001, which are used to suppress fires without damaging sensitive equipment. Lastly, regular inspection and maintenance, as outlined in NFPA 25, ensure all these systems stay functional and reliable over time. Connecting all these points, it's clear that a comprehensive fire protection approach involves multiple systems working together, each critical to safeguarding lives and property. Let's take a closer look at how we determine the number of detectors needed for a fire alarm system based on NFPA 72 guidelines. The key formula here is quite straightforward. We divide the area in square meters by 81. So, for example, if you have a 500 square meter space, you'd need approximately 7 detectors. This helps ensure proper coverage without overloading the system. Now, when installing these detectors, there are some important key points to keep in mind. The maximum spacing between detectors should be 9 meters, which ensures that no area is left unprotected. Call points should be installed every 45 meters to allow for easy manual activation in case of emergency. And of course, the sound level must be at least 65 decibels A-weighted, so alarms are clearly audible throughout the space. Regarding installation, the process starts with wiring all the components properly. Then, you mount the detectors at their designated locations, fit in the call points, and finally connect everything to the control panel. This sequence ensures a reliable and effective fire alarm system that adheres to safety standards and provides peace of mind. Let's take a closer look at fire pump design according to NFPA 20. First, the flow calculation is based on multiplying the area by the density. For example, if we have an area of 2,000 square meters and a density of 4 liters per minute, the flow would be 2,000 times 4, giving us 8,000 liters per minute. Converting that to liters per second, it's approximately 133 liters per second. Now, moving on to head calculation. The total head involves summing up 3 key components: pressure, friction, and elevation. Pressure is the force needed to push the water, friction accounts for resistance in pipes and fittings, and elevation considers the height difference the pump needs to overcome. When it comes to installation, proper setup is crucial. You start by fixing the pump securely on a stable base. Then, align the motor properly to ensure smooth operation. Next, connect the suction and discharge piping carefully to prevent leaks or air pockets. After that, install the controller to manage the pump's operation. And finally, test the header to make sure everything is functioning correctly. All these steps and calculations are vital to ensuring the fire pump performs reliably when it's most needed. They tie into the overall goal of designing a safe, efficient, and compliant fire protection system. Now, let's look at the fire tank design according to NFPA 22. The key formula here is that the tank volume equals the flow rate multiplied by the time. For example, if we have a flow of 9,000 liters per minute over a duration of 60 minutes, the total volume needed would be 9,000 times 60, which equals 540,000 liters. That's approximately 540 cubic meters. When designing the tank, there are several important steps to ensure safety and functionality. First, we start with a concrete foundation, which provides a sturdy and stable base. Next, we install an anti-vortex plate inside the tank to prevent vortex formation during water withdrawal, which could otherwise cause turbulence and damage. Then, there's an overflow component to prevent the tank from overfilling, protecting against potential spills or structural stress. Finally, a leak test is essential to verify the integrity of the tank before it becomes operational. These steps are crucial in ensuring the tank functions reliably and safely, aligning with the overall goal of effective fire protection. Now, let's talk about sprinkler design according to NFPA 13. One of the key formulas we use is flow, which equals the area multiplied by the density. This helps us determine how much water flow is needed for a specific area. Another important point is the spacing between sprinklers. The area served by each sprinkler can be calculated by multiplying the spacing in one direction by the spacing in the other, giving us the area coverage per sprinkler. For example, in an ordinary Hazard A classification, the required flow rate is 140 square meters times 8 liters per minute, which totals 1120 liters per minute. When designing the system, there are several essential steps. First, install the branch lines, then fit the sprinklers onto these lines. Next, flush the pipes to remove debris. And finally, conduct a pressure test at 1.5 times the working pressure to ensure everything functions properly. These steps are crucial to ensure the system is reliable and effective in case of a fire. Remember, proper design and installation are the backbone of a fire-safe building. Now, let's talk about fire piping, specifically referring to NFPA 13 and 14 standards. When calculating head loss in fire sprinkler piping, we use this formula. Head loss is approximately 10.67 times the product of the length, L, and the flow rate, Q raised to the power of 1.85, all divided by the pipe's coefficient, C raised to 1.85, and the diameter, D, raised to 4.87. In this case, we're assuming a steel pipe with a C value of 120. This calculation helps us understand the pressure loss due to friction as water moves through the piping system, which is critical for ensuring proper water flow and system performance. Now, moving on to the installation process, the first step is to lay out the main or riser. Once that's in place, we use grooved fittings for connecting sections. These fittings make assembly faster and maintain a tight seal. After the piping is assembled, a hydrostatic test is essential. This is where we fill the system with water and check for leaks or weaknesses. Following that, we drain the system, and finally, label all valves clearly. Proper labeling ensures quick identification and operation during an emergency. All these steps are vital to ensure the fire piping system is reliable, efficient, and compliant with safety standards. Let's now look at smoke control according to NFPA 92. The key formula here is Q equals 0.188 times a raised to the 1.5 power, times the square root of H. This might look complex at first, but it's really about understanding how much smoke needs to be vented out. A, of course, is the smoke layer area, which is essentially the size of the smoke layer itself, and H is the height from the floor to the top of that smoke layer. For example, if we have an area of 300 square meters and a height of 10 meters, plugging those into the formula gives us a Q, or airflow rate, of approximately 534 cubic meters per second. Now, in practical terms, this means we need to install exhaust fans capable of handling this volume of smoke. Once these fans are installed, they're connected to a control panel that manages their operation. Next, we add intake vents to ensure proper airflow, so fresh air can enter as smoke is exhausted out. Finally, testing the fans is crucial. Usually, we test them at high temperatures, around 300 degrees Celsius, for about an hour, to make sure they can handle real fire conditions effectively. This overall process is essential for maintaining safety and controlling smoke in emergency situations, which ties back to our overall theme of comprehensive fire safety management. Let's talk about the clean agent system, specifically NFPA 2001 standards, including FM 200 and NOVIC 1230. The main purpose of this system is to protect rooms that house sensitive equipment where water-based suppression isn't an option. This might include data centers, server rooms, or laboratories. The key calculation for designing this system is the design concentration, which is the percentage of agent needed relative to the room volume. It's calculated by dividing the mass of the agent by the room volume and then multiplying by 100 to get a percentage. For example, if we have a room with a volume of 200 cubic meters, the typical concentration for FM 200 would be around 7 to 8%. Another important aspect is the hold time, which should be at least 10 minutes. This ensures the agent stays effective long enough to suppress the fire completely. Both FM 200 and NOVIC 1230 are designed to achieve this hold time reliably. Now, let's go through the installation steps. First, you need to install the cylinders with nozzles and pipes according to the manufacturer's layout. Proper placement is crucial for effectiveness. The second step is connecting the control panel to the fire alarm system, typically interfaced through NFPA 72 standards. This allows for quick activation when a fire is detected. Next, perform a door fan test to check for leakage, following NFPA 2001 Section 771 guidelines. This step ensures the system will hold the required concentration without leaks. Finally, record the amount of agent used and the pressure within the cylinders, which is essential for maintenance and future inspections. Overall, designing and installing a clean agent system involves careful calculation, proper installation, and thorough testing to ensure reliable fire suppression without damaging sensitive equipment. Now, let's talk about inspection and maintenance according to NFPA 25 standards. First, the schedule is key to keeping the system reliable. Weekly, it's important to check the pump pressure and panel indicators to ensure everything is functioning properly. Then, on a monthly basis, we should test the sprinkler valves and flow switches to confirm they're responsive. Quarterly, it's recommended to perform flow tests and record the pressure readings, which helps us track system performance over time. And finally, an annual full system inspection is essential, along with preparing a detailed report to document the condition and any needed repairs. Moving on to maintenance tips, these are simple but effective. Regularly cleaning detectors and nozzles prevents dust buildup that could impair detection. Exercising valves ensures they open and close smoothly when needed. Replacing any damaged hoses or washers is critical to prevent leaks or failures during an emergency. And always, it's vital to log all tests and results. This documentation helps us track trends and demonstrates compliance during inspections. Remember, consistent inspection and maintenance are the backbone of a reliable fire protection system. Staying proactive helps us identify issues early and maintain the safety of everyone in the building.